Hello, everyone, and welcome to today's session of InfluxDB IOX Tech Talks. Super excited to see all of you here for the first Tech Talks all about InfluxDB IOX. My name is Caitlin Croft. I work here at Influx Data, and I'm very excited to see all of you here today. And we have Paul Dix, Andrew Lamb, as well as Ed Robinson, who have been the ones building out InfluxDB IOX. So they will be presenting today. Feel free to post any questions you may have in the chat. And of course, you can always unmute yourself and ask them questions as we go. This session is being recorded and it will be made available on YouTube later today, as well as on our website. So if you have to drop off at some point, no worries, you can go and check out the recording. So without further ado, I'm going to hand things off to Paul.
All right, thanks, Caitlin. Let me do a screen share. Let's see, where are we? Where are you, Chrome? All right. Let's see. All right, can people see that? Yes. All right. So my session is going to be very brief. Basically, I just wanted to give a project update on IOX to say where we are. For those that need a refresher, IOX is basically our new core of InfluxDB written in Rust using Apache Arrow. One way of describing it is essentially as a columnar database using object storage as persistence, but it's actually many other things. So when I was thinking about how to do this project update, I was actually struggling a bit because a lot of the work has been kind of like foundational work. And it's kind of hard to describe if you haven't actually been inside the guts of the thing. So I am going to try and like give a little bit of overview information. So some of this may make a little bit more sense. And I'll be following this up with a blog post that will kind of talk about these concepts in a bit more detail. So basically, these are the four major work items we had over the course of the past month. And number one is backward compatibility and integration, basically making sure that you can query IOX with Flux and InfluxQL. Andrew has been doing that work. The in-memory columnar store, which is actually not hooked up to anything yet, but that basically means that we can work on data. We can have data in a compressed representation in memory, so we have more of it, and we can execute queries very fast. That is called the segment store. And Ed has been working on that. A bit of work on the data lifecycle, which is basically a new write-ahead log buffer and capturing data from an in-memory database over to Parquet files. And then lastly, a bit of work on Apache Arrow Flight, which is the RPC mechanism in Arrow. So basically contributing to the Rust libraries there to get it to a point where we can use it for communication between IOX servers when transmitting query data. So let me talk about some of these pieces. So integration, this is kind of what it looks like. So IOX has a gRPC API, which is not something that we want to have as part of the public-facing IOX API, but it's something that we have in our own storage layer in our Cloud 2 offering. And basically, this is how other components in our cloud offering talk to the storage stack. So that's either the Flux query processor or the InfluxQL processor. They talk to the storage service using this gRPC API. So what Andrew has been doing is he's been basically reverse engineering that API to hook it up to our in-memory database within IOX. So you can basically communicate to IOX as though it was that same storage service. Later in a future point release of InfluxDB to open source, we'll have a connector using the same gRPC protocol to be able to communicate to the IOX servers. So this is a bit about how data is organized. And the reason I chose to show this slide is because I need a way of describing how the data lifecycle works, but also what the segment store is and why it's important and all these different pieces. So, logically at the top, you have a database, so just have like my data, for example. That data is logically split out into partitions. In this example, I have like a partition per day, but essentially partitions are basically all data that share a partition key. So as data is written into the database, a partition key gets assigned per row, which can use the measurement name. It can use tag key value pairs. It can use a formatted string of the time. It could use parts of individual field values like pulled out via regex. But basically you have all this data split out into partitions. And the goal of arranging data in these partitions is to make it so that at query time, we can rule out large chunks of data from the query to be able to determine what we need to actually process. And then beneath partitions, you have things called chunks. So basically a chunk is an immutable collection of data, right? So it could be data that's spread across many tables, or it could be an individual table. But basically it's just a block of immutable data. So you could potentially have many chunks per partition, because a partition really is never closed for writing. Like you can always write data to a partition. For example, if you're doing historical backfill, even if you have data organized on a day-by-day basis like this, you could potentially have late arriving data or historical data that you're writing in. So the chunks thing basically play into this data lifecycle concept, right? So at the top you have the ingest, and when we're ingesting data, we can do one or both of these two things. We can write it into an in-memory write-ahead log, which is basically just a buffer, or we can write it into like a write buffer database, which is basically an in-memory database that is optimized for being able to accept writes, but it's also queryable. Then later, what happens in the lifecycle is those buffers get captured into immutable things. So on the wall side of things, you have basically a segment, which maps to an individual file in object storage. And on the queryable data side of things, you have chunks, and basically a chunk underneath a chunk, it could be either a collection of Parquet files and object storage, along with basically some metadata that summarizes what's in those Parquet files, basically the schema and the summary statistics like the min value, the max value, that kind of stuff. Or you have the segment store, which is, again, basically just an in-memory columnar database that's highly optimized for basically query speed and compression. So all these underlying pieces, we're kind of like implementing these pieces individually, like kind of in an isolated way, and they're not really hooked up yet. I mean, the write buffer piece is hooked up and the gRPC bits are actually hooked up, but the things like the wall segment and wall buffering and the segment store is not really hooked up yet, but we'll be getting to those bits, over the course of the next month or so. So that's basically what we've been up to this month, which is kind of hard to describe. I hope that made a little bit of sense. I will try to spend more time on it in my blog post, but I'm sure the question that many of you are asking is, when can you actually use this thing? Obviously, we're not producing builds yet. We don't have documentation. We are trying to structure the open source repo in a way that you can actually build it yourself if you want to. And we're starting to get more issues in there, and we will be labeling issues as basically good issues for first-time contributors who want to come in and add to the project. But like I said, all of these underlying components are gradually coming together and being built up towards getting them all into the server with an API that makes sense. So our goal is to actually start producing builds with a fully functioning piece of software by late January, early February. So those builds won't be for production use. They're basically just be for people to be able to test it out, to play with the API and see how the thing works, and start to try and get a feel for what kind of things you can build with IOX. Yeah, so that's all I have. We'll probably jump right into Andrew's talk and then save the Q&A for after that if there are questions related to the project updates or Andrew's talk as well. So let me stop my share. All right, Andrew. So I guess I should introduce Andrew. Andrew Lamb is one of the creators of IOX along with myself and Ed Robinson, and he is now an expert on Rust and Apache Arrow.
Something like that. Thanks, Paul. Yeah, and I'm all right. So let's get going. Can you all see this still? I hope. I'm just going to assume you can, unless someone tells me.
We can see it. That's good.
Cool. So, like Paul said, I'm going to talk a little bit about Rust and Arrow and how that is, just so you get some sense of my background. I spent, I don't know, several years working as on the query optimizer at a columnar database called Vertica. So I saw sort of the guts of the query of what a analytic database system looked like. And my background in addition was a bunch of like systems programming, and then I've been doing sort of higher level systems architecting stuff the last couple of years. But I'm super psyched to get back into the database internals. So I'm coming at this from a very strong database background. And basically my goal today, especially drawing on some of that experience, is I just want to like explain to you what Arrow is. Eventually I'll get there, but I got to set it up as to like why it's a good thing for making a new database. I'm going to start with random opinions from my own background, and then I'll get into Arrow, and eventually I'll show code about Arrow and Rust and try to convince you that Arrow is a good thing. So I think if you look back at the history of databases of the last 15 years, despite lots of vendors trying to have like one database to rule them all, it's basically gone the opposite direction, where there are many different databases for various different data models. This is, by the way, just off the top of my head. I'm sure I missed some of this. So please don't give me too hard a time for not being an exhaustive list. The deployment topology, whether you want pure cloud or some other options, obviously the use cases, there's a million of them, ecosystem. And so basically the point is, over time, people are willing to put up with new database systems because typically if you pick one of these sort of special cases, you can get 2 orders of magnitude better, and people are absolutely willing to do that. I certainly didn't come up with this. If you guys want to read someone who wrote it had a much more coherent way of saying it, there's a paper from 2005 that talks about sort of, at that time it was like Oracle was trying to convince everyone to put all their data in Oracle, and they're basically make the argument that one size does not fit all. And I think we've basically seen that out over the last 15 years. So of course you might imagine that's partly a justification now for why we're building yet another database, right? Because there's certainly plenty of databases in the world for both time series and other kinds. This is a link, these slides, I'm sure we'll share them at some point. This is just a link to the blog post announcement that goes into it in much more detail. So, that's what we're doing. It's focused very much on, it's a specialized database. One of these trends, as Paul talks about, it's for in-memory column. It's an in-memory column store, but it's designed for sort of time series. And I'll talk more about that in a couple of minutes. I think I also just want to take a brief pause. I'm not going to spend too much time talking about this slide, but when you talk about databases, I at least group them up, but there's at least 2 big categories. And I'm basically going to talk entirely about analytic systems and the things that are good about those. So basically a bunch of the stuff I'm going to talk about would be terrible for a transaction system, right? Those would be like, the OLTP systems is the name, the classic name for them. But like key value stores is a more modern version. But effectively their workload is large numbers of transactions per second, changes per second. But each one of the changes updates a very small amount of the data. Right, so that's the classic Oracle stuff, but it's also Mongo, Dynamo, whatever. On the other side, there's analytic systems, analytic databases, big data. OLAP was like the old school way of describing that. But basically, the workload is fewer transactions per second, but each one of the transactions or queries touches a much larger chunk of the data. So basically, I'm going to talk the rest of the talk about analytic systems. That's very much what IOX is in sort of how I categorize it. So the point is, you wouldn't use Arrow to build a transaction system, right? That's one conclusion you can come away. So I think something I didn't fully appreciate when I started working on databases was that there's a huge amount of stuff that you need to build. Basically, if your goal is to build a specialized engine, focus on your specialized use case, make it super fast, get a lot of users. A lot of people don't realize it actually takes a huge amount of effort just to get to like a point where someone will even recognize your software as a database, right? You need to have a way to get the data in, get the data out, like store what tables it is, describe what types all the columns are. None of that's like particularly special to your database, right? That's just something, it's kind of like table stakes to get the database to a point where people will even understand that. Oh yeah, you gotta have a client API, right? And so here was my sort of brain spew this weekend. I just tried to, I'm not gonna read all this, right? But this is my attempt to try to show a timeline of how you go from deciding you want to build a database to eventually like to the point where you've got a really, really cool one. So, you know, you would start, you have to come up with some way to store the data in memory. Like I mentioned, you've got to, you know, record somewhere what tables you have, what columns they are, what data types they are. You've got to actually codify that type system somehow. Basic bread and butter of an analytic database is doing filtering and aggregation, right? So taking the rows, filtering them down. You've got to deal with when people want to do this, you know, concurrently. You probably have a query language, arithmetic expressions, like to add the columns together, for example, or perhaps compute predicates on them. You've got to have some story for persisting, client API. You know, you probably need some kind of heuristic query planner, you know, and at that point, like maybe you have something that looks like a database, but like all this stuff, probably you're not going to innovate on, right? This is just basic this table stakes. And then you'll discover things like date time expressions and the love and the joy there, right? That's far more complicated than anyone ever anticipates. You probably start doing more advanced analytic techniques like operating on the compressed data. You'll discover joins at some point, and both the joy and the pain of that. That's effectively what I spent, you know, 4 of my years of my life out on Vertica, was discovering the joys of joins. And then, you know, at some point you'll realize as soon as you have joins, you need a cost-based optimizer because you have more choices of what you can do. So you need to pick one. Then you'll discover outer joins, subqueries. Anyway, I can go on and on. Eventually, maybe you'll do your advanced analytic queries. You need a bunch of different language clients. So like, this is all just trying to explain how much work it is to build a database in some ways. Oh yeah, you'll discover at some point people actually want to run queries on data that don't actually fit in the amount of main memory you have. So you've got to, you know, handle that. Anyway, so I swear this talk is about Arrow, right? And the point, like the connection on this slide to Arrow is, if you look at what Arrow lets you do, I think it's effectively to shortcut a bunch of this sort of table stakes basic pieces that you need to build any analytic system, right? So it's, you know, I put green arrows and dotted arrows, kind of depending on how you look at or how you define these semi-vague terms. Arrow covers a big chunk of them. So I think, at least when I saw Arrow, like I've seen a lot of similar things to Arrow in proprietary systems before and other database systems. And it's really cool to be able to sort of, someone's taken that, made an open source project out of it, and then you reuse that foundation so that we don't end up spending a huge amount of time reinventing, you know, yet another columnar store that you have to, you know, implement vectorized expression evaluation on, because that's frankly not where a large amount of innovation is going to come from, I think, at this point. Hopefully that makes sense. Yeah, so, you know, when Paul first was talking to me about what, you know, the project that became IOX, it sounded really cool. And he said, oh, I've read this thing about Apache Arrow, right? And like, I went to the website, as one probably does, and you read this, right? You look at some of the talks that are on the web about Apache Arrow, and Wes is talking about it. And like, it's actually not as obvious, you know, if you read this picture, like, what is this? And you look at Wes McKinney, who's the founder of this, he's talking about like the machine learning ecosystem and the data analytics, and like, you know, how in the world is that related to a database? Right. So I think, yeah, you know, that's kind of the summary if you Google around the web of what Arrow is. And obviously the point of my talk is to try to explain how that's connected, but I think I've already made the point. So specifically, how does it do that? So here's I'm sorry for this, right? This is like bastardized Rust, but I couldn't I couldn't help myself. So the toolkit for modern analytics, well, let's talk about the kinds of tools you would need to build a modern analytics database. Obviously, the first thing you need is some reasonable file form. Like, you need some way to persist the data onto disk. It's probably going to be columnar. It's got to be compressed, right? You're going to be dealing with large amounts of data. Arrow has that in in Parquet, right? Parquet was a file format that predated the Arrow project, but it's subsequently been absorbed into it. So it's got a columnar, good compressed file format. You need some way to represent your data in memory to take advantage of modern CPU architectures. Almost all analytic systems are vectorized, which basically means they operate on vectors of data, like they operate on arrays of data at a time rather than one individually. We'll talk about that maybe a little bit more. So Arrow has that. It's arrays. Again, it's nothing like magical. You'd all come up with it yourselves if you thought about it for any length of time. But the point is, it's all there. You don't have to rethink and reinvent the wheel. If you want to do things like, add two columns together element-wise, again, like that's not a hard piece of code to write, but you start doing it with all the various different types. Now you maybe want to do cast and string operations and timestamp stuff. Like it just becomes a significant amount of investment to do. And Arrow has that. They're called compute kernels. And of course, if you want to transfer this stuff over the network, you need some amount of machinery effectively to not only transfer the bytes, but also transfer information about what types they are and whatever operations you want to do. There's actually other cool stuff in Arrow that I want to talk about, but maybe as part of another tech talk, because this one's already going to be pretty long. So anyway, so this is like sort of the high level, lots of cool stuff in Arrow. And I think what I'm going to do now is I'm going to try to eventually get to now I'm going to try to connect the dots between InfluxDB line protocol, right? So this is, if you're not familiar with the data model that InfluxDB has, it's also one of the data models that IOX will support. And I basically just want to spend a few minutes describing how you map this stuff into columns, right? Because I'm talking about how Arrow is so great for working on columns of data or whatever. You need to be able to, understand how you go from influx to columns. So as a super brief primer, there's much better stuff online, but the line protocols are made up of it's a record-based data model, right? So each one of these records, lines represents a different record. They consist of a measurement followed by some number of tags, which are name value pairs. The values are always strings. And then you've got some number of fields, which are, you can effectively think of them as additional attributes on this record. They can have more very different data types like strings or floats or ints or whatever. And then you've got a timestamp column as well that are nanosecond, precision timestamps since the epoch. And again, like I said, there's plenty of better stuff online if you want to learn about line protocol. There's just, I think, enough to then show how it maps into the IOX data model. And again, IOX data model is important because IOX data model is a columnar store. And so that's how we're going to connect line protocol to the use of Arrow. So there's measurements. Measurements turn into tables in the IOX world. This isn't going to be shocking, but the tags turn into columns. In this case, there's a column with the tag for each one of the distinct tag names. And the values of the tags are just stored as values in the columns. The fields likewise turn into columns, and then so does the timestamps. So, again, this is not earth-shattering stuff, but what's kind of important is part of the reason why you can do much better in time series use cases is because you can make assumptions about these various, you effectively have columns of data that have different properties, right? So like tags, at least tend to be in the historical workloads, very low cardinality string columns, right? So like the InfluxDB existing engine takes very significant, advantage of that property to get its performance. And likewise, the timestamps have properties that you can use to compress them and operate on very, very efficiently. So anyway, this is the basic mapping from line protocol to the columns of data, right? And so now, given we've got columns of data, now I'm going to go show some examples of the Rust code that you would use to operate on those columns of data. And like the thing that I'm still not, I'm not 100% sure I've convinced Ed about this, maybe I'll convince more of you, is that if you're going to write one of these analytic systems or analytic databases, you're effectively going to end up implementing the Arrow feature set anyway, even if you might not think that at the beginning, right? And I'll try to point that out over the next couple of slides. So the way I'm going to do this is I'm going to compare both the plain Rust implementation and then Rust using the Arrow implementation. And I just want to please don't send me hate mail, at least not too much hate mail about performance comparisons or whatever. I'm well aware the plain Rust is not what you'd write in production, right? That's kind of the point. But I think I just want to show you, like, I had to have some numbers in here to make me feel like a little bit of an engineer. The other point that I almost forgot when I was doing earlier versions of these slides is I'm talking about like basically the software engineering benefits of Arrow. Like, it's basically going to save you a whole bunch of time in your project. There's a huge additional benefit of interoperating with other tools, which I'm not going to talk about, but it's another major benefit of Arrow. So let's talk about the kind of example the kind of operation you would do in a typical database, right? Typical analytic database, you're going to go compute some aggregate on a bunch of the rows, but first you're going to find all the ones that are not in US West, right? This is some example previously, right, from my, basically doing predicates on this column. Okay, so let's talk about how we do that in Rust, right? Like, so this is the simplest thing I could come up with in Rust. To do it, I hope, if you're not familiar with Rust, I'll try to walk you through it very briefly. This basically says I'm making a vector of strings. Each of these strings has its own allocation. It runs through, 0 to, I think I set this to 10 million or 100 million rather on my local laptop. And then, every third string we make it into a string and stick it into a vector, right? So that's that. When I did that on my laptop this weekend, it took 600 milliseconds for 100 million elements. Right? Now here's how the same thing you do with Arrow. And sort of the point of me showing you this is that it's, if you squint not too hard, this is approximately as ergonomic as the raw Rust. Yes, you have to use a builder, right? This is a Rust sort of common pattern. But here you go, you're effectively enumerating, you're running over all the tag values again. And for each one, you're doing the same thing, right? You pick one of these values, and rather than, directly making a string out of it, you're appending it to this builder, and eventually you finish. You end up with this array thing, right? So, I don't know, I did this on my laptop, basically the same amount of code, and it's actually faster. Now, again, this, like, if you were doing this for real, those of you will immediately notice, well, there's no reason to do an additional allocation for one of three, constant strings all the time. That's a terrible idea, which I agree it is. But as I'll show, like, as you make it more sophisticated, your code just gets more and more complicated. So, like, basically my point is the reason this is faster is because Arrow is not allocating something, each one of these strings. It's just like has a pre-allocated vector that stuffs them all in a compact form. But that's cool, right? I didn't have to write any of that. I just had to use a builder to build it up. So let's compare the memory footprint, right? Like, how much memory does that use? This is some very simplistic version of calculating how much memory is used for each one of these strings, right? You take the size of the actual vector itself, plus for each one of the elements in the vector, you basically take the overhead of the string plus the bytes, the actual length of the string, which, since it's ASCII and the capacity, like, I realize this methodology is probably not ideal, but I think it's close enough to give the point. And I know, unsurprisingly, you end up with something like 320 megs for my 10 million items. There's some function call that does the same thing in Arrow, and actually, very amusingly, you immediately see it actually uses half the memory. And again, the reason it's using half the memory is because Arrow effectively doesn't have the overhead of each one of these strings each time. And again, all you smart coders, I'm sure you can do even better than this, probably without thinking too hard, but it's definitely going to get more complicated. So in a typical database, you wouldn't just sort of like make an array of strings, right? You're actually now, let's compute the predicate. So the way that's often represented in a database is you run over the array of strings and you compute some bit set, right? You compute another array that's of Boolean values of which rows passed the predicate and which ones didn't. And so here's the very sort of simplistic Rust way of doing it, is that you go over that string vector that we made before, and for each one of the elements, you use this comparison and you collect, and then you can count. This sort of counts how many of them pass the value, pass the predicate. And when I did on my laptop, it's quite fast, as you might expect from Rust. It was 50 milliseconds. It seemed pretty fast to me. I don't know. Here's the equivalent version of this in Arrow. Right, again, this is kind of cool, right? There's already there's a function that says, I want to take all the elements in this array and I want to compare them to a UTF-8, string basically. So you just run this function and you immediately get the bit set. So it's, as I would claim, as ergonomic as Rust, possibly even more so, because you don't have to worry about element by element. And you get basically the same thing. In this case, I'll wave my hand and say, actually Arrow didn't do so hot here. It's quite a bit slower. But I hope to convince you in the real world, like, it's not actually, so now it's not a fair comparison. Let's talk about some of the stuff that Arrow is doing that Rust is not doing. So for example, you probably have to handle nulls, right? So let me just add more complexity to the example of how you would handle nulls. Again, not that this is shocking, right? But this is, you're actually, in Rust, you'd encode that as an option string probably. And you'd write, here's the code that you'd write to, you effectively have to check in the Rusty kind of way whether or not something's null first. You can do this and it's still quite fast. I think one of the things that's kind of cool is that Arrow sort of already handles all that null stuff for you, right? So in my mind, right, that's a lot more ergonomic. I didn't have to worry about nulls. By the way, that, if I may opine just for a moment, that was a classic other thing I saw when implementing other database systems, is like, you get all excited, you'd implement it for like the not null, just normal case, everything would be great. And you think like, well, what's all this other complexity of other systems? How hard could it be? And then you have to go back and implement like proper null handling semantics. And that like just makes all your beautiful code, well, this isn't even that bad, right? But like nulls make all your beautiful code much, much less beautiful. Same thing with joins, by the way. Joins would be much, much easier without nulls. Here's another thing you're going to do. I'm not going to belabor all these, but once you've computed the, when you're doing database processing, you've computed the filter of which rows passed. So you have a bit set, and now you're going to basically you're going to take the rows that passed and combine them into a contiguous array for subsequent processing, right? So that's effectively what this is doing, right? It's running over each one of the elements in the bit set we found earlier, and if that element passed, it's copying to the new vector, and that makes whatever. It takes 450 milliseconds to do that. Yeah. Arrow, you can do the exact same operation. There's already a kernel that does it. It's called filter. It's slower. I mean, it's faster rather. Again, this delta is entirely about not having to allocate these strings. I realize like I'm basically taking the same advantage over and over again, but I didn't have to do any additional coding to take advantage of it. All right, so I don't know if that was the most compelling example of types of things that Arrow just sort of has implemented already, but I'm happy not to have to write them, or at least not write too much of them. We're actually working on some of the Arrow implementations, so like, let's talk about something even maybe more efficient, right? Like here's something that Influx does or is talked about doing, and if you thought about this for a little while, you'd for sure think like, well, if you're building a specialized time series database and the tag values are relatively low cardinality, right? Like, so there's relatively few numbers of distinct values for each one of the columns, you'd probably not actually replicate the same string over and over and over again, right? You'd probably do something more like store pointers to the string, right? And a classic way to do that is with dictionary encoding. So you have a dictionary as one sort of list, and then you actually store the values as indexes into that dictionary. So this is a representation of the first location is US East, second one is US Midwest, third one is US West, and then it goes back, right? So then it's US East, US Midwest, US West. So it's the same data, just encoded in a much more efficient way. Each one of these, depending on how many elements are in your dictionary, can be quite small. I picked U8 because that's pretty good. I'm not even going to try to write the raw Rust code to do this. If you want to, it's a fun exercise, but it's not that interesting. You could use a library maybe to do it. But I think the point is Arrow actually already has this built in. It's called dictionary encoding types. And I think this code is basically the same as the original code to build the Arrow array that we did before. The only difference is the setup of the builder is different, right? So in this case, you have to tell Arrow what types of values you're storing, strings in this case, what basically what the type of the dictionary is. what the type of the keys are. In this case, I'm going to say it's 8-byte integer or 8-bit integers rather. You build the builder, and then this loop that actually puts the strings in there is exactly the same. So that's already kind of cool, right? It's like I didn't have to worry about now having to pass, like if you just think through some of the implications, right? Now you want to pass values like this around, you've got to pass a pointer to the dictionary and the location, and like your processing has to handle both of those. And it's not impossible, but it gets pretty complicated pretty quickly. And using Arrow, you just don't have to reinvent that, but you might have. So speaking of other things, you might, oh yeah, that's the other thing. If you do this, right, basically with almost no additional Arrow code, now I've shrunk the overall memory footprint to 10 megabytes, right? Again, not using anything out of beyond basic, CS 101, but it's already all set up there. And it fits nicely with, and there's compute kernels, right, that operate on this type already. So I don't know, I'm feeling good. A lot of stuff I didn't have to write. So another example, right, as you're going along and implementing your analytic database, you would for sure at some point decide that you've heard about these SIMD instructions, right, that the modern processors can do operations on multiple array elements at once rather than doing one at a time. Right, that's one of the things that processors have been getting better at over the last however many years. So for sure, right, like one of the things you'll add to your analytic systems is taking advantage of SIMD. And you probably already know where this slide ends, but let me just walk you through it. And I don't know, maybe for those of you who aren't as familiar with SIMD, I'll just try to give a brief introduction. So this is the setup is I'm trying to compute the elements in the output where the left hand array is bigger than the right hand array. Right? So I'm just basically running down each one of the elements in this array, finding where the green one is bigger than the blue one. And so in a SIMD kind of way, you can use instructions that are native to the processor to compare multiple elements in one CPU instruction. And the number and exactly how it works depends on the size of the data and what processor you have or whatever. But in this example, I'm showing that you could actually compute this in 4 chunks, right? You compute it with doing these 4 in one instruction, these 4 in another, these 4 in another, and then you have to do kind of the remainder in a fourth, right? So again, this is absolutely something you do trying to get performance out of your system. You can guess that Arrow already has it, but the even cooler thing is you don't have to do anything special, right? Arrow already has this stuff built in, and so if you want to compute the greater than operation onto arrays, here's how you do it in Arrow, the Arrow library, and someone else has already gone through the trouble of like actually implementing this. I'm definitely not going to try to explain all this because I don't, to be honest, probably that wouldn't be the not sure how well I'd do. But this is just, I just took this out of the comparison kernel, and I don't know, maybe it's obvious to other people, right? But to me, this is sort of like the kind of thing you'd get to once you got your basic database sort of table stakes there, and now you'd realize, all right, now I got to bump performance to the next level. You'd start implementing things like SIMD. Again, you wouldn't, it's not like you can't do this. It's pretty straightforward, but it's just a bunch of time, and you have to do it for all the different data types and whatever. So hopefully that made sense, and you didn't, I don't know, maybe it was valuable. This is like yet another example of the types of operations that you might want to be doing in a database. And of course, Arrow does basically all of this already. I might be making it sound too obvious, but I think at least my experience was, in other systems, and you can kind of see other open source projects, I think, fall prey to this, which is they have a neat idea, right? I'm going to build a database for whatever, and they don't realize that up front they're going to have to do a huge amount of work to even get to the point where they can actually start specializing. And so I think Arrow is a very compelling story to be able to take a well-designed library, we're contributing to it as well, and then use that to really accelerate the initial implementation. I've of course been extolling all the virtues of Rust and Arrow, and I haven't talked about the caveats, like not all those kernels, certainly not all the kernels are SIMD implemented, not all of them are implemented for various data types. There's a bunch of other stuff we're actively adding. But I think at least my analysis was we're much better contributing back upstream and using that sort of both benefiting from the ecosystem and contributing back to it than we would be just trying to re-implement it ourselves. Again, I'm not 100% sure I convince everyone that that's the case, but I think as you go through and you sort of implement more and more of a system, you more fully appreciate what Arrow has to offer. Yeah, and so I think Paul might have mentioned we've been investing specifically in things that I think are more beneficial to influx data, right? There's lots of stuff in Arrow, but we've been focused on getting IPC up to the point where we can send data back and forth when we start using, I think our goal is to use Arrowflight as the IPC mechanism in IACS, and I think we just need to get the library a little more mature in that area. Also, dictionary and datetime support, unshockingly, are going to be really important for IACS, and so we've invested a bunch of time there. And then there's also a thing called Data Fusion, which is it's effectively a query engine, so it's another level on top that allows you to plan both SQL, but also sort of other higher level operations that aren't just like low level arrays. But I'm going to talk about that in another talk, I think, because this one's already pretty full. So yeah, thank you. It's still very early days. Paul mentioned there's lots of cool stuff we're still implementing. It's all open, which is also pretty cool. So I don't know, hopefully that wasn't too fast. I was a little worried about time, and I think maybe I've jammed it too fast, but I think we do at least have time for questions.
So if anyone has any questions for Paul or Andrew, feel free to post them in the chat area of Zoom, or you can also unmute yourself and just ask them directly. And there will be another session of InfluxDB IACS Tech Talks in January. This will be happening every month. So I will drop a registration link in the chat for next month's.
Yeah, if anyone has specific things they want to hear about too, I'd love to, I have stuff I could expound at length on, but I have no idea if people find that interesting or not. So anything you want to hear, I'd love to hear feedback too.
And we always love hanging out and chatting with our community. So of course there is the InfluxDB community Slack, so you can go and join it. There is a InfluxDB IACS channel where you can talk specifically about this project, but then of course, everything else under the sun related to InfluxDB, there is a Slack channel there. So it's a great resource. We also have our forums. We're all on Twitter as well if you're reaching out to us there. And then of course we have lots of other avenues. We have other webinars and virtual time series meetups. So here's a question. How do you determine which data goes to the WAL buffer versus the write buffer? What happens when parts of your data set goes to those two paths? What does the compatibility look like across those paths?
I can answer that one. So basically the configuration of IACS server, you define a database, and for each individual database, you can define what components you actually want to use. You don't need to use like almost all of those paths are optional. So for instance, you could have an IACS server that takes in data and just buffers it in a write-ahead log in memory, which then subscribers can pull from, or it just buffers it and then offloads it in segments to object storage. And literally, like, that's all it does. It never handles queries. It never does anything else. Separately, you can optionally have, the IACS server store the data in memory in a form in that write buffer database that's basically queryable. The thing about the write-ahead log is it's not queryable. The only thing you can do with the write-ahead log is basically subscribe to the stream of data that it has. Now you can certainly, there will be functionality to filter out that stream, but there's no way to like say like, here's a SQL query, execute this and like give me back an answer. So if you want to do that, the write buffer in-memory database can do that in an area that's still hot for write, right? So you can turn that on or off depending on what you want to do. And it's not mutually exclusive of the wall. So you don't even need to buffer data in memory. You could literally just write it in, it gets stored in that in-memory database, and then whatever. Like it can operate purely as an in-memory database with no persistence whatsoever. So basically managing that lifecycle of when data is buffered in the write-ahead log in memory and when it's sent out to object storage, and also when the index data in memory is converted over to Parquet files for longer term storage and like partitioned out. Again, that's all configurable and it will be controllable by the API.
Does the write buffer handle read queries like memtable, like an LSM tree?
Yeah, so the write buffer is basically just in memory, and you can query it. I mean, an LSM tree is a bit more lower level. Like you'd build an actual relational database on top of an LSM tree, whereas and the other thing is the LSM tree includes persistence, right? It has its own write-ahead log, and it has like memtables and SS tables, which are the immutable files. The write buffer database it has no persistence whatsoever. It is only an in-memory structure for storing tabular, tables of data that you can then query using SQL through the data fusion layer that Andrew was talking about. The persistence is kind of like separated out. So yeah, basically like anything that's in the write buffer database is actually in memory. So any query you send to it is executed purely from memory. Yeah.
When can we expect to see InfluxDB IOX being available for testing in InfluxDB Cloud?
So we have a target to offer that early in Q2. Basically, it's just an alpha for people who want to opt into it for testing purposes. We want to be running it obviously for our own usage earlier than that. But for people who would want to actually opt into it and test it out in an alpha state, Q2 is our target. Next year. So,
is it true that partition keys are not required to reference timestamps?
That is correct. So partition keys are a little weird. So basically, again, part of the database configuration is you say like, as data arrives, generate a partition key using these rules. And like I said, the rules could be like, you do nothing, in which case like every piece of data has like an empty string is the partition key, right? And it's all just there. You could use a measurement name or table name, or you could use any one of the pieces of actual data, and it's done on a row by row basis. So in line protocol, it's a line by line basis. So the thing is like that happens as the data arrives and the partition key is generated on an individual IOX server. That data can then be replicated other IOX servers, which if they so choose, can generate new partition keys or use the partition keys as they exist. But that only happens on write. And basically that determines how data is organized basically in memory as it arrives, and then later how you then convert that data into Parquet files that get persisted to object storage, right? Because that partition key becomes part of the path in object storage. Now, all that being said, you can change how partition key is generated over time. And the partition key really only matters for the write section of the data lifecycle. For reading data, basically, if you're pulling it from object storage, there's the raw data files themselves, the Parquet files, but there's also basically index files that show that for each partition, there will be these chunks. And for each of those chunks, you have these tables with these columns of these data types and the min and max of those and the count, right? So essentially, what the query planner will do is it will look at that partition metadata and that chunk metadata to determine which ones map to the query. So if you change how data is partitioned later, like one, you don't need to reshuffle it in object storage. You can just like read it on an as needed basis. But yeah, I'm not sure if any of that made sense. But basically, like partitioning it's kind of like it's something that can be fluid over time. And unlike in other databases where if you change your partitioning scheme, you end up like remapping all your data, you don't need to do that in IOX.
Perfect. You mentioned that new chunks can appear later due to backfills. Does it mean that different chunks can have overlapping or interspersed timestamps?
Yes, they can. So in InfluxDB, basically the primary key for any individual row is basically the measurement name, the tag set, and the timestamp, right? So that's the primary key for the row, and basically each one of the field values shares that exact same primary key. So what that means is for that you can only have one value at that given timestamp. Now, IOX will allow you, it doesn't currently, but it will allow you to define what you want as your primary key, right? Under the covers, IOX makes no distinction between tags or fields. A measurement is actually a table of data. So basically you'll be able to define a primary key. Now, if you choose to define your primary key as the tag set and the timestamp, then basically what will have to happen is if you write in a new chunk that has the same primary key as data from a previous chunk, that will need to be resolved at query time, right? So basically you're talking about deduplication. And then you would want to later, compact those two chunks into some other chunk that has that resolved, right? Because that kind of like deduplication is expensive to do over time. Like ideally you're in a situation where you're not doing that. So if you're going to write in another chunk and it's going to be like colliding with previous data, which essentially, again, is like you're rewriting history in that case. You're taking a previously captured event or measurement and you're rewriting that thing. So if you're going to rewrite history, we'll have methods so that you can actually do that in a way so that you won't have to do the deduplication at query time, which can be expensive.
Did you consider integrating Arrow into the existing Go InfluxDB codebase instead of starting from scratch in Rust?
So the nice thing about Rust is it actually doesn't preclude us from doing that, right? We could import, the entirety of the library side of IOX and all these database pieces and stuff like that into the Go runtime, the InfluxDB Go runtime. And that is something we may still do. I'm kind of like, I'm a little bit allergic to the idea, but so there were a couple of reasons. Like one, the structure of IOX as a database is totally different than InfluxDB, regular InfluxDB, right? Regular InfluxDB is this like inverted index paired with this underlying time series storage thing, whereas IOX is tables of data partitioned in a way so that we can answer queries really, really fast by ruling out large swaths of data and then brute forcing the rest. So the structure is completely different. But the other thing is we had some other design constraints that we wanted to operate under, right? So we wanted no memory mapping of data files so that it'd be easier to operate in a containerized environment. We wanted very strict control over memory usage, and basically being able to limit like how much data a wall would take, how much data a specific index, or how much memory a wall segment or index would take. So we wanted that kind of like fine-grained control. So basically all of that stuff means like essentially it's like a completely different core. So we're doing it as a separate project because we want those things, and obviously the strict memory control we wouldn't be getting exactly in Go. So yeah.
Perfect. What are your plans for concerning the persisted Parquet file catalog? Do you plan to use Data Lake / Iceberg, or do you plan on developing a custom solution?
I mean, so our goal is to basically just use raw object storage, right? So basically put, get, delete, and list, and organize the file structure in such a way in object storage that we'll be able to read efficiently from it, so that we don't have to read the entirety of object storage or do, list all the files to be able to figure out what's there. It certainly doesn't preclude us from integrating from other data lake kind of solutions. I can't remember, like the Dremio guys are pushing something forward. I can't remember what that is. That's maybe Iceberg. So we could certainly integrate with some of those things, but it isn't something we're looking at specifically. I mean, it's absolutely a design goal of using object storage in the Parquet files. Is we're hoping that will be an integration touch point with other systems, right? So if you want to process that data in EMR or other data lake solutions, you'd be able to do that, and IOX would play nicely with those things. But to be honest, I don't know those systems well enough to know what those integration points are yet.
Can you elaborate a little bit on what's different about the data layout in InfluxDB IOX versus InfluxDB? For example, does a unique tag value map to an inverted index entry?
Yeah, so it's, I talked about this just a little bit earlier, but yeah, it's completely different. There's no inverted index in IOX. So basically the unique tag values, like I said, the way you partition the data is how the query planner will figure out which partitions it needs to hit to execute a query. And then within a partition, the strategy is essentially to do a combination of brute force and also just intelligent execution. The work that Ed's been doing on the segment store will basically make it so that, you have a specific tag value that you're looking up, it can map it and figure out what the dictionary ID is, and it'll be able to process that very, very quickly. And again, the reason we've designed it that way is kind of two things primarily. One, we wanted IOX to be able to work with essentially unbounded cardinality, right? We wanted it to be able to be used as a backend for tracing data or highly ephemeral data or whatever. And then the other is to make it so that it could actually perform analytical queries across higher cardinality data without falling over, right? And that, I mean, that's basically why it's structured like that.
All right, we're going to take one more question, and then hope to see you all next month, the next session. How will indexing work in InfluxDB IOX? Can you index any column in the database?
Yeah, so the only thing you really have is Andrew's got to jump really quick.
Yeah, I got to jump really quick, but I just wanted to weigh in here
Photobomb.
Yeah, thank you. Great. Sorry, that was my son. Basically, most analytic systems tend to have very minimal indexes compared to transaction processing systems, and it's because in an analytic system,
Photobomb.
Maybe I'll answer this later. In an analytic system, the data volumes are so big that if you actually have significant other types of index types, you end up consuming more memory, and they basically consume more resources than your actual data. And so pretty soon the actual cost of maintaining them, both in terms of memory, disk, and then also just performance when you're adding them, it doesn't work out. So IOX, the goal is to effectively be self-indexed, right? So the way you do that is you are very careful about how you store the data in the primary storage, keep it sorted and keep it sufficient metadata to rule out most of it. Sorry about the photobomb.
No worries.
Nice. Yeah, that's basically the partitioning piece. But separately, you could certainly build your own secondary indexing system outside of IOX. And again, the integration, using object storage as the actual store, the idea is you'd be able to pull the Parquet files or pull the wall segment files directly from the object storage and build other secondary indexing if you wanted to. But at the outset, we have no plans for secondary indexing, because again, the idea is your data is partitioned in such a way that a query will come in, will rule out most of the data, based on how it's partitioned and based on even for the individual partitions, like I said, we have metadata that describes what's in the partition. So the planner will be able to use that to rule out partitions. And then within the partitions, basically just brute force it really fast.
All right. Well, thank you everyone for joining today's InfluxDB IX Tech Talks. I hope to see you all next month at the next session. Once again, the session has been recorded and will be available on our website as well as YouTube later today. Thank you.
Thanks, everyone.